This is Eric Ranchard. I'm the president of the European Society of Medical Imaging Informatics. I'm very happy to be able to welcome everybody to this USOMI webinar. Tonight we have a very special speaker. This is Sebastian Weingärtner from the University of Delft, Delft University of Technology. He is assistant professor there at the Department of Imaging Physics, and he works in a lab called MARS, which is the Magnetic Resonance System Lab. So he is specialized in analyzing and or developing biomarkers and in MR imaging, especially for cardiac, but also for other purposes. And this is mainly the topic he will talk about today. So the topic is turning pictures into numbers, which refers to quantitative imaging, of course. Sebastian has completed his PhD in 2014 at the University of Harvard, Harvard Medical School, and also at the University of Heidelberg. His thesis was mainly on quantitative T1 mapping of the heart. He also worked as postdoctoral researcher at the University of Minnesota, the Heidelberg University, and Stanford University before moving to Delft. So he also received some recognitions for his work on cardiac MRI, among which a fellowship by the Life Sciences Research Foundation, and he was also named junior fellow of the International Society of Magnetic Resonance in Imaging, which is quite impressive, I must say. So Sebastian, I would like to give the word to you, but first some more logistic information. We do have the possibility at the end of this lecture to ask questions, to have a discussion. For this purpose, there is a Q&A box in the bottom of your screen. So please do not hesitate to ask your questions, to write down your questions, and we will try to discuss them afterwards. So this is the way we should proceed, I think. And then, of course, I also have to say a word of thanks to Bracco, the company who is sponsoring this webinar and making it possible to organize this. So thank you for being here, and please, Sebastian, I give the word to you.
Thank you, Eric. Thank you very much for the kind introduction, and hello, good evening, everyone. And I do have to start with a small confession. Indeed, it turns out the title, Quantitative Imaging, Turning Pictures into Numbers, was a little bit of a clickbait. Indeed, it should be more accurately described as Quantitative Magnetic Resonance Imaging, Turning Pictures into Numbers, because we will almost exclusively talk about magnetic resonance imaging. So if you are allergic to MRI, now is the time to disconnect. For those of you who decided to stay, the good news is I have no conflict of interest to declare. But I do have some interest in sharing some learning goals with you in the next upcoming 30 minutes or so. What I want to discuss with you is that I convince you that magnetic resonance imaging is actually worthwhile. It's greatly suited, particularly for quantitative imaging. I want to discuss with you the aims of quantitative imaging and provide you an overview of the contrasts that can be quantified with MRI. Next, we're going to look at 3 steps that are involved in obtaining quantitative MRI images. And finally, we're going to conclude with some clinical and research examples of quantitative MRI. So let's dive right in there. I'm sure most of you have seen these before because there's a number of amazing imaging modalities that all enable unique insights into the human body. CT and X-ray, for example, has great imaging resolution and is really fast, but offers poor tissue contrast and ionizing radiation. PET and SPECT is another one, which is really fast, has great contrast because we receive signal only from tracers, but it has a very bad resolution and still the ionizing radiation is there. If we move to ultrasound, for example, we are still fast and safe, and it's widely available, and resolution is pretty decent. However, the penetration is very limited, and most of all, it's operator dependent. MRI finally has a very, very large contrast spectrum, as we will see later on, provides great resolution, and has no ionizing radiation exposure to the patient. However, it suffers from long scan time. So overall, this looks like all of these methods have their ups and downs in comparison to each other. But what I like to think about when I compare these methods is, where do we actually want to go with medical imaging? And there I would like to point your view to a recent sci-fi movie from 2013, Elysium, which pictured the vision quite clearly. Here, a young patient is placed into the scanner, and briefly after a sweep over, the scanner automatically detects the disease and provides a diagnosis. Now, this is pretty impressive, and I find the main reasons why this is impressive is because the medical imaging modality features 4 components. It's non-invasive, it's sensitive enough to pick up the disease or a number of diseases, it's comprehensive enough to not only show one variation and one potential disease, but a number of these, and finally, it's readily evaluable in that sense that it automatically puts out a diagnosis. If we compare our imaging modalities to this vision of medical imaging, the situation looks quite a bit different. CT, for example, is not non-invasive, might be very sensitive to some changes, but not very sensitive to others, so it's not very comprehensive. But therefore, it's quantitative and easy to evaluate. PET and SPECT is again not non-invasive, might be very sensitive, but again, it's not very comprehensive because some effects are not visible in PET or SPECT at all, but therefore it's readily evaluable. Ultrasound fares a bit better, it's non-invasive, and it provides contrast that might be comprehensive view of a lot of changes. However, it might not be very sensitive to some remodeling, and it's really hard to evaluate due to the operator dependency. And that's where MRI comes in. It already checks most of the boxes. It's non-invasive, it's very sensitive to remodeling in the body, and it provides a comprehensive view because of the large contrast spectrum. And finally, the only drawback is that it's really hard to evaluate. So the big question that I want to address in this talk is, how do we make MRI images more interpretable and evaluable? And the answer to this question is quantitative MRI, in my opinion. And to convince you that this answer is legit, I want to do something that's a little bit frowned upon in science often. I want to borrow a method from business, which in this case is called the golden circle. The golden circle is a logical way of thinking that questions the legitimacy of the brand. So that sounds quite suited to what we want to do with quantitative MRI. So I thought we can give it a shot. So what do we do in the golden circle? We ask the why, the what, and the how of quantitative MRI. And this is what we're going to do throughout the next 25 minutes of the talk. So why do we need quantitative imaging in the first place, the first question? There's a number of reasons, but I think I want to put these 3 convincing reasons forward first. I think quantitative imaging enables us to reveal diffuse information. It also enables to disentangle signal contributions and finally provides standardized post-processing as an opportunity. What do I mean by this? Let's first look at the revelation of diffuse information. I always very much like to show this example for that. MRI is really good in showing focal changes. For example, if we look at this line, we see everything looks perfectly fine because the fruit flesh is very homogeneous. However, if we compare it to this lime, we see, oh, there's something substantially wrong. In this case, the lime suffers from seeds. And this is depicted in MRI greatly because we can compare the signal in the seed to the surrounding signal in the healthy reference of the fruit flesh. Now, the same thing happens in the human heart very often. For example, this healthy subject shows a homogeneous signal throughout the myocardium. On the other hand, the LGE images of a subject with HCM in this case display focal variations, in this case caused by scar, which is an indicator for disease remodeling. However, it's not always that easy. If we compare those two lines, for example, on first glance, both were pretty well intact. The signal is very homogeneous in both of the flesh or of the fruits. However, only a closer look with quantitative MRI enables us to reveal some differences. And actually they're quite marked, and it turns out that the right one isn't even a lime, it's just an orange in disguise. And the same thing can actually happen to real-world images of the heart as well. Again, we have two subjects. One of them, and both of them depict homogeneous signal throughout the myocardium. But when we quantitatively compare the T1 times in both of them, we see something is wrong with the subject. And it turns out this case suffers from a disease called thalassemia major. And only quantitative MRI enabled the depiction of this. Indeed, this is not only a toy example, but the introduction of quantitative MRI in thalassemia major had quite a clinical impact. The reason for this is that iron overload was a common cause of death in the disease, but effective treatment for this condition existed in form of chelation therapy. What was lacking, however, was efficient means to non-invasively diagnose that. When quantitative T2 star mapping was introduced, it enabled the depiction of iron overload and caused an overall 60% drop in overall mortality, as almost all deaths in iron overload could be prevented. So quantitative MRI and the revelation of diffuse changes can actually be very clinically impactful. But there's other reasons. Let's look at disentangling signal contributions. Let's move away from the heart and take a look at the brain, for example. Now, on the left-hand side, we're presented with a diffusion-weighted brain scan. That is a qualitative image. On the right-hand side, we have a quantitative ADC map. On first glance, we could be deceived and show that the two provide very similar information. Like, for example, regions that are dark here are depicted bright in the ADC map. And similarly, regions that are very bright show dark signal in the ADC map. In this case, in the diffusion-weighted imaging, bright signal can be caused by a lack of diffuse motion, which shows up as black in the ADC value. However, on closer examination and comparison of those images, we see that there's other bright areas in this image, for example, up here, which actually do not correspond to a marked decrease in ADC. Now, that raises the question, what's going on there? And actually, it turns out this qualitative image, the voxel intensity, is a signal that reflects a number of properties, not only diffusion, but also T1, T2, coil sensitivities, and many more. So there's various reasons that can make a voxel bright or dark. On the other hand, the quantitative maps eliminate the influence of those confounders and provide the quantification in SI units in this case. That means that dark areas necessarily correspond to less diffusion and bright areas to more diffusion. So in this sense, quantitative imaging removes the potential for conflating a number of factors in the interpretation of MRI images and makes the results much more interpretable. But it also enables standardized post-processing. What I mean by this is that one of the major drawbacks of MRI is that depending on the vendor, the scanner, the equipment, or sometimes even the sequences, images that are supposed to show the same thing can actually display quite distinct visual appearance. Now we have greatly trained radiologists usually that are trained to look beyond these differences among the images and recognize the disease underneath. However, even for those greatly trained radiologists, this reduces the interpatient and intrapatient comparability. When we move to quantitative imaging, however, the image appearance is unified across systems, sequences, and scanners. And this not only eases the post-processing for our greatly trained radiologists, but also enables the possibility to use standardized post-processing. Specifically in the time of machine learning, this is a great asset because now data can be pulled from many sources and many centers, which provides us a much larger basis for training neural networks. This is particularly of interest as MRI in general deals with rather small data sizes compared to other areas of machine learning. So in this sense, quantitative imaging could be seen as a way of providing the Hounsfield units of MRI, and therewith be a gateway to the efficient use of machine learning in MRI. So now that we know why it could be good to quantify with MRI, the question arises, what do we even want to quantify, or what can we possibly quantify? And that's quite a complicated answer, because MRI has such a large contrast spectrum. So let's try to get to the bottom of this contrast spectrum. The reason why it is very comprehensive is that MRI happens across a lot of different scales and orders of magnitude in size in biology. So let's start with the wavelength. Depending on the field strength of our scanner, the wavelengths can range somewhere between tens of centimeters and meters. So that's pretty gross. However, the resolution turns out to be much finer, around a millimeter or even sub-millimeter resolution. And imaging smaller with imaging resolution much shorter than the wavelength is actually what warranted the Nobel Prize for Lauterbach and Mansfield. However, we even have smaller scales that we are dealing with, and these are the signal sources, which are commonly the H1 nuclei. And together, these span about 11 orders of magnitudes, which is quite a range. But the result of MRI happening across all these orders of magnitudes is that we can actually also create contrast sensitivity to different biological effects at all these scales. So let's take a look into an example of this. For example, if we look at tractography in MRI, we trace a signal across multiple voxels, and this spans tens of centimeters across a whole organ. So that's definitely a large scale. In the centimeter scale, we often look at motion. For example, in the heart, when we trace cardiac motion, this is more in the order of 1 centimeter. We go even smaller to the millimeter range. Quantitative susceptibility mapping is an example, because it sensitizes the signal to contributions from larger vessels. Smaller vessels in the capillaries, on the other hand, they play an important role for fMRI, and even a smaller scale on cell size we deal with is important for diffusion imaging, as we've seen before. If we go much smaller, we now approach the size of macromolecules, which are important for chemical shift imaging or assessing fat fraction or a number of other factors. And at the smaller scales, we actually can look at properties of the hydrogen nuclei itself, which actually influences the most commonly used properties, for example, proton density, T1 and T2. So this is not meant to be comprehensive, and we're going to see much more contrasts, but it's just a mean to illustrate on what effect scale we can actually cover with MRI. And usually these are categorized in 3 different groups. Macroscopic scale is everything that happens larger than the imaging resolution. Roughly on the order of the imaging resolution, we call it mesoscopic effects, and everything much smaller is the microscopic effects. So because there are so many contrasts, and it's virtually impossible to present you with all of them, I thought it might be reasonable to instead try to classify the contrasts that we can quantify with MRI and how we quantify them. So let's attempt a taxonomy for this. We already looked at the effect scale. So for example, diffusion imaging is, as we have heard, on a microscopic scale, while flow imaging happens on a macroscopic scale, where we trace bulk motion of blood, for example, across tens of centimeters. But there's also another dimension, for example, the evaluation scale. That means, are we processing the information voxel by voxel, as we do this in T1 mapping, and we usually refer to this as mapping because we obtain quantitative maps, or are we looking at the information image by image, for example, if we get volumetry from cardiac cine MRI? We can also think about the contrast source. Where's our signal coming from? This could be either endogenous or exogenous. Endogenous, I mean anything that comes from within the voxel and within the pool that we are studying. For example, T2 mapping, where the signal really comes from the spins within the voxel. However, exogenous can be either something related to an exogenous contrast agent, for example, gadolinium-based, or also related to a signal that is created outside of the region of interest or the slice of imaging, for example, the time of flight approach. We can also look at the signal type. Are we dealing with images, for example, when we're accessing fat fraction maps, or are we creating a spectroscopy, spectrums, for example, in phosphor spectroscopy? Another dichotomy would be the detection. Is it directly measurable? So does a property directly affect the signal that we are detecting, or is it a surrogate measurement? An example for this one would be measurement of pH value with MRI, where we're actually measuring the kinetics of molecules that are tightly bound and pH sensitive, and use a calibration curve to calculate the pH value from those kinetics and their effect on the signal. And finally, we can look at where does our signal come from. Most often these is hydrogen nuclei, but there's also a number of other nuclei that are commonly imaged that we subsummarize as X nuclei. And an example of this would be the tissue sodium concentration. Now, this was a lot of information to digest, and also it's roughly the time, the average time span of concentration during a PowerPoint presentation. So I would suggest we take a 5-second break while we look this blissful hedgehog floating around. So now that we are all re-energized and revitalized by this blissful hedgehog, I think we can tackle the next question, which would be, how do we make MR images quantitative? And I always like to propose to introduce that as a 3-step approach. And as a beer lover, I always very much like to use the beer example for this. Let's assume we want to quantify the decay of beer foam. What we need for this are 3 steps. Firstly, we need a fit model that describes the kinetics of the beer foam. We then need qualitative images. In this case, we can just measure the height of the beer foam over time at multiple time points. And finally, the last step will be fitting the qualitative images to the fit model. Now, you might think this might be somewhat of a toy example, but I want to give you a hint to the scientific relevance of this problem. It's so relevant that 2002, the exponential decay of beer foam was actually awarded the Ig Nobel Prize. And even more excitingly, since then, it has been put into question whether the model is really a single exponential, and Apollonian decay was also proposed. However, enough for the beer foam. In MRI, the situation can be even more complicated at times. Often our fit models are based on the block equations, but sometimes this is not enough to model, and exchange kinetics or even the Solomon-Blomberg equations need to be taken into account. But having the model, how do we get the qualitative measurements? So this is a realm that's usually called pulse sequence development. And there we're trying to create different contrasts, often by using preparation pulses such as inversion or saturation modules, but also diffusion gradients or a number of other ways. And having both in place, what commonly is done for the fitting is, for example, widely used the Back-Marquardt approach, at least a nonlinear least squares fitting, or dictionary matching, but also model-based reconstructions and more advanced methods can be used. So let's put this into practice. How do we actually use the 3 steps to become quantitative? And for this purpose, let's take a look again at our old friend, the diffusion-weighted image. How do we get the lovely ADC map out of it? So it turns out that a diffusion-weighted flash sequence can be well described by the block equations with this fit model. So that looks like quite a beast. So let's tear that into parts first to understand the fit model better. We have 3 components in there. The first one is a number of tissue properties, for example, the spin density, T1 and T2 star relaxation in this case, and then finally the ADC, which is what we want to look at and what we want to quantify. But there's also a number of other properties, for example, a scaling factor K that includes, among others, the B1 minus field and the flip angle alpha, which is driven by the B1 plus transmit field. So these system parameters also play an important role. And finally, maybe not in this case, but in many other cases, also physiological parameters such as cardiac motion, respiratory motion, or stress and rest play an important role in the state of the signal. Those last 2 categories are often subsummarized as nuisance parameters. So the question is now, given all these influences, how can we disentangle the signal contributions to arrive at quantitative maps. And I think this can be nicely explained by looking at two different approaches that I would like to introduce at subtracting or adding information. So let's look at the subtraction idea. The purpose is that we subtract all the unnecessary information out until we are left only with what we want to quantify. This is practically done by acquiring multiple images where the only variation among the images is related to the parameter that we want to quantify. In this case, we got 3 diffusion-weighted images with different b values. So the only cause and difference of the signals is caused by a difference in diffusion properties. We already see that if we were to divide the images by each other, these parameters that we are not interested in would all cross out. And the same thing happens if we perform a fit to them. In this case, though all these parameters that we are not interested in can be subsummarized as one weighting parameter, which gives us a low number of degrees of freedoms in the fit and enables us to quantify the ADC. So this method is most commonly used, not only in diffusion, but also in T2 or T2 star mapping and T1 mapping. And the advantages are that usually few images are required, as we only have a small number of degrees of freedom in the fit. And also it offers certain resilience against unmodeled factors, because often they cancel out or can be subsummarized. There's another approach though, which I would like to call the addition approach. The idea here is different. The idea is that we add so much information to the image until we can all have enough information to resolve everything without canceling it out. So let's assume we have a signal that is dependent on T1, T2, and the diffusion. We get a number of images with different weightings among these factors, and we jointly fit a fit model that incorporates all of these properties. What we are left with is the joint quantification of these properties, of all 3 properties. So this method became popular when magnetic resonance fingerprinting was introduced, but a similar approach, only adding the information subsequently, is also used in CEST or QBOAT, where we first map out nuisance parameters and then feed them into a final fit. The downside of this is that more images are required, and often this leads to longer scan time. The upside, on the other hand, is that it leads to joint multi-parameter maps. But there's also a big risk that we are taking, and I want to caution you about this. This method can actually yield false friends if we don't account for all confounders in the addition method. Taking an example look at this image. That's a semi-quantitative M0 map and can easily be mistaken for a proton density map. However, upon closer examination, we see that the signal is much higher in the front of the brain than in the back of the brain. And we really hope this is not true for a proton density map. And it turns out, actually, it wasn't a proton density map, but the field bias, the sensitivity of the receive coil, actually played a major role, causing this signal to be much larger. Only after subtracting this out, or from the semi-quantitative map, we actually obtain a quantitative proton density map in quantitative units. And that's the major key learning I want you to take away. If you ever see a quantitative MRI map with no units on the color bar, it might as well be that it's not very quantitative because a number of confounding factors might not have been accounted for. So you should indeed be skeptical about that. Now, for the end of the talk, let's talk about a few examples of quantitative MRI, either in research or the clinic. Now, these examples are not meant to be either comprehensive, exhaustive, or representative. I purely chose them based on my personal liking. That's why let's start with myocardial T1 mapping. The idea of myocardial T1 mapping became apparent when we looked at T1 contrast after contrast agents were injected into the heart. Turns out that these contrast agents accumulated in scar tissue because the extracellular volume in the scar expands due to cell death, and furthermore, the washout kinetics are reduced. So after time, a higher contrast concentration is retained as compared to the healthy myocardium. Then imaging this with an inversion recovery sequence turns out that this enables the depiction of scar as bright hyperenhancement against dark background of a healthy myocardium. Now, T1 mapping is somewhat of the natural extension of this, where we say, hey, what if we get multiple images on the inversion recovery curve? And we actually take a quantitative look at these scar images. And it was first proposed with the hope to actually quantify scar and also diffuse fibrosis with this method. T1 mapping first became clinically viable with the introduction of MOLI, which enabled the sampling of multiple inversion recovery experiments with a few single-shot images triggered to the end diastole. So that already provided high-quality T1 maps in a single breath hold. It gained further clinical traction when SHMOLI was introduced, and since then a number of sequences were introduced that mostly focused on single-slice mapping during a single breath hold, and often were based on saturation or inversion contrast and used single-shot imaging. However, all of those methods converge to about 3 modes of operation. The original idea of post-contrast T1 mapping turned out to be not very reproducible. The problem there was that the signal depended not only on the washout of the gadolinium contrast agent, and therewith the time after contrast agent injection, but also on renal clearance and a number of other factors, besides the volume of distribution. However, on the bright side, native T1 mapping, which is quantifying the T1 times of the myocardium in the absence of the contrast agent, turned out to be a very useful clinical imaging biomarker, as it's sensitive to a number of macromolecular changes, including fatty or iron deposition, but also a number of other things. A third mode was introduced by combining native and post-contrast T1 mapping with a hematocrit value that yielded the extracellular volume quantification. So this finally gave us a biomarker that was related to the extracellular volume as we hoped for the depiction of scar, but at the same time was much more reproducible than post-contrast T1. Native T1 mapping and ECV mapping became widely used in clinic, as it turns out they are very sensitive to a number of cardiomyopathies, and by now have been tried out in almost all cardiomyopathies that are out there. Extremely sensitive they were shown to be in amyloid, in iron overload or Fabry's disease, but also other disease entities benefit. And the clinical value was judged that high that now the cardiac mapping starts to be integrated into the first clinical guidelines, and advanced cardiac MR centers routinely use them in most of their protocols. So let's try to apply some of our newly acquired knowledge and try to categorize native T1 mapping. So the effect scale is microscopic because the T1 relaxation happens on a microscopic scale, which is the exchange between spins and the lattice. But we evaluated voxel by voxel to yield a quantitative map in the end. The contrast source is endogenous because the signal indeed comes from the spins itself, and the signal type is by processing one image after the other. We directly detect it because the relaxation is directly reflected in the signal that's required, and luckily it's based on the hydrogen atom. ECV mapping, on the other hand, poses quite a different prospect. It's still microscopic and voxel-wise, but the contrast is partially exogenous because of the use of an exogenous contrast agent. It still uses imaging, but it's only a surrogate marker because we're actually imaging the effect of the contrast agent on the signal rather than the volume of distribution directly. But it's likely still based on the hydrogen nuclei. So a second example would be quantitative myocardial perfusion. Myocardial perfusion is based on the idea that we track the signal following the injection of a bolus of a contrast agent. What we usually observe is first the right ventricle lights up and the left ventricle, and then slowly the myocardium enhances. People found out, though, that quantifying this perfusion might not only provide the possibility of objective and faster and simpler assessment and post-processing of this data, but particularly also enable the assessment of a global reduction in flow. But it's not that easy to quantify myocardial perfusion. In addition to the perfusion images, we also need the arterial input function, which is kind of the response of a generic tissue, in that case blood, to the inflow of a contrast agent. The problem is that's not easy to image both at the same time, because the arterial input function measured in blood has very high concentrations of gadolinium, which often leads to a saturation of the signal, while the myocardial signal change is marked by much lower gadolinium concentrations. Two approaches are usually employed for thus obtaining both informations. One is a dual bolus approach, where two contrast injections are performed, one with a lower contrast dose and the other one with a higher contrast dose, where the first one is used to obtain the arterial input function only, and the second one is used for perfusion imaging. A second approach would be a dual sequence approach, where the idea is that we get both in the same sequence and after a single bolus injection. In order to compensate for the signal saturation, the arterial input function is obtained from a separate measurement within the same sequence, where multiple echo times are obtained, which then allows to calculate back and estimate the signal despite the presence of saturation. Having obtained this arterial input function with either method allows us then, via deconvolution of the myocardial signal and the temporal footprint of the myocardial signal, to generate quantitative myocardial blood flow maps, as presented here. And those prove to be clinically useful, not only because they reduce artifacts, but also allowed for assessment of microvascular disease and enabled inter- and interpatient comparability. So how do we classify quantitative perfusion? It's a macroscopic effect for once, because we are actually looking at the inflow of perfusion from the coronary arteries. It's still evaluated voxel by voxel to obtain quantitative maps, but it's an exogenous contrast because we're actually imaging the change caused by a gadolinium contrast agent. We base it on images. It's not spectroscopy, but it's a surrogate marker, because what we're actually measuring is the signal change caused by inflow of a contrast agent rather than the actual myocardial blood flow. Finally, it's still based on the hydrogen nuclei. Let's look at the last example before we adjourn this talk, though, which is called electrical property tomography. The idea of electrical property tomography, or EPT, is that the interaction of all electromagnetic fields with biological tissues is actually driven by the Maxwell's equations. And the Maxwell's equations contain the permittivity and the conductivity as parameters. So the initial idea was, hey, maybe if we map out the electromagnetic field very accurately, maybe we can estimate the electrical properties of the underlying tissue. The beauty of this approach, and why I wanted to present it, is that in this case, we're actually mapping a B1 field, which we formerly considered a nuisance parameters. But it turns out that if we succeed in calculating permittivity or conductivity from this, we actually obtain useful information about the tissue out of this. So how do we reach these maps? What is required is usually a 3D mapping of a B1 field, but actually of both components, the magnitude and the phase. The magnitude is often measured of the B1 field in many circumstances, and multiple viable methods exist, including double angle, Bloch-Siegert, and many more. But the phase is somewhat harder to obtain. And what's commonly done here is using the reciprocity assumption, which means that the signal phase from the receive and the transmit coils of the transmit-receive channel are the same. If we have this hardware and this assumption, we can then back calculate on the phase of one of the B1 fields. Given the magnitude and the phase, we have multiple approaches that we can actually obtain the quantitative electrical property maps. We can either base them on B1 plus maps or on B1 minus maps, and there's a number of different underlying formulations that we can use for the quantification. But all these methods eventually yield similar results, which boil down to this conductivity map as shown below. In this case, it was used for imaging of a tumor in the breast, and it turns out that for cancer imaging, electrical properties is very useful, because in this case, it enabled a clear depiction of the tumor, just as clear as it would be only obtained with contrast-enhanced imaging, but no exogenous contrast agent is needed for EPTs. So if we kind of categorize that, it's a little bit harder because the effect is mostly on a mesoscopic scale, meaning happening between neighboring voxels. However, we can still process this as mapping voxel by voxel, and the contrast is endogenous because it's caused by the interaction of the tissue itself with the B1 field. The signal type would be imaging in my book, but it's a surrogate marker because what we're measuring is the impact of the B1 field rather than the actual electrical properties. But we do get this on the hydrogen frequency. So let's summarize. I hope you got some of the following points in the talk. And what I try to communicate is make you sensitive that magnetic resonance imaging is actually a great modality and is greatly suited for quantitative imaging. I hope you understood the aims of quantitative imaging, which is the why behind the brand, and also gained an overview of quantifiable MRI contrasts, even though there are many, many out there that we didn't talk about. I hope you have seen the 3 steps involved in obtaining quantitative MRI and have gotten a glimpse into some examples in the clinic or in research with quantitative MRI. If I didn't succeed in communicating of any of these learning goals, it's not that bad either, because there's a great upcoming resource by the ISMM Quantitative MRI Study Group that I also used as inspiration for most of the material of this talk. And it's an invited submission to MIM and hopefully will be submitted sometime throughout this year. So I would urge all of you to take a look into this once it's going to be published. Finally, I want to thank everyone in my lab who contributed to the slides, and it's great to work with. And I also want to take the opportunity to shamelessly advertise that we are hiring. If you know someone who might be interested, Delft is a great place to do MRI research, and I'd be very glad to get in contact. I also want to thank my sponsors, and most importantly, I want to thank you for your attention. And in these special times, I would also urge you to stay safe and healthy. And now I'm very much looking forward to receiving questions.
All right, thank you very much, Sebastian, for this very interesting and fascinating presentation. To be honest, for me, being a radiologist, this is a bit out of my comfort zone. I'm less into the technical aspects, as you probably can imagine. So I can see that the audience is also quite mixed. We do have a mix of radiologists, clinical physicists, people from technical medicine, and there's a lot of other attendees as well. So unfortunately, at this moment, I don't see any major questions. Of course, there is a question if the cited publications, if it would be possible to provide a list of those publications. Maybe we could do that if they can send us a written request to do it, and then we might be able to answer by email afterwards. But nevertheless, I do have a question for you. Of course, you are doing excellent work in doing quantitative analysis of MRI images and MRI information, which is undoubtedly very important. And the importance of quantitative data is certainly increasing, also from the perspective of radiologists. But my question is, first of all, how do you decide what kind of biomarkers are useful? What are the use cases that you are looking for?
Yeah, that's a very good question, because very often, but in our own research in particular, if we are trying to quantify things that have not been quantified before, it's very hard to say whether it's sensitive to the disease remodeling we want to look at or not. So I think the first resource to look at and to decide what biomarkers are worthwhile to quantify are the physical underpinnings, where we look at the pathophysiology and the results of MRI relevant physics markers. Like one example would be oxygen plays a big role in fMRI, for example. So everything related to oxygen can always be taken into consideration when we look at MRI signals. And there's a number of these things where we know of physical links between properties and the signal. And if we know these links and we can also link them to the pathophysiology, I think this is a promising candidate for an imaging biomarker. But in the end, only clinical evaluation will show whether the biomarker proves to be clinically useful or not.
Yes, exactly. I just wanted to repeat, if there's any questions, please do not hesitate to send them to us in the question and answer box. Okay, I can see a question now coming in from Fahid Malikian. And the question is, which type of MR sequences are more common to use in clinical brain studies for T1, T2, and T2 star mapping?
So that question is a little bit hard to answer. It's a good question because I have focused on cardiac mostly. Point being is that quantification in the brain is not as commonly performed as in the heart. So many centers decide on them by themselves on what sequences to run. And I'm not sure whether quantitative MRI, quantitative relaxometry is actually part of the guidelines for neuro MRI.
Mm-hmm.
I'm not entirely sure about that.
Yes.
Mm-hmm.
I might have another question for you. Yes.
Maybe very briefly, just to give a few examples of
oh, yeah, sure. Go ahead. Sorry.
A few examples of commonly used techniques. Definitely magnetic resonance fingerprinting gained traction and is used in a number of labs now for quantification of T1 or T2. Jointly, some MRF sequences also enable the quantification with T2 star. And other than cardiac images in the brain, other techniques that are widely used are not based on preparation modules, but rather on steady state signals. And the despot methods are used to be very widely used there. Especially for T2 or T2 star, also other methods, including Gesse or so, find application. Yeah, but it's definitely distinct from the cardiac methods.
Okay, I will ask you another question. So there's a lot of research going on, of course. My question actually is, when do you think these quantitative analytic tools will be available in clinical practice? But to my experience, this is still pretty, let's say, limited, most in academic environments or research environments. But how do you think these tools will be implemented in clinical practice, and what time do you think will be needed? How much time will be needed, and what is the major hurdle to do it?
That's a great question. I think luckily we do have a great role model of this, because myocardial T1 mapping and other cardiac mapping techniques actually went through this long and bumpy road, and it definitely is a long and bumpy road. I mean, the initial Molly paper was 2004, and it started to become really popular about 2010. And now it's actually a clinical product that's widely usable by even people out, like basically the standard MRI scanners nowadays ship with these sequences, so it can be very widely used in any hospital. But given these timescales, that easily spends 10 years. And as you say, there's major hurdles to take. I think there's mostly two translational gaps, and I would like to point to this to the study group paper as well for more insight on this. But the two translational gaps that I see there is, firstly, methods are often developed in a physics research lab, and the first gap will be for the method to actually leave the lab and be used by other groups, even just other groups of researchers or collaborating clinicians. This is essential, because otherwise the use won't be widespread enough to ever demonstrate a clinical value. Beyond this, though, once it is used in selected groups, I think what needs to be considered is not only that it's clinical valuable, this can be shown in a number of patients, but that's also cost effective. And this then usually requires very large studies and a lot of time. And only if it's finally been proven to be cost effective, it could be a consideration for routine clinical use. But I guess from the mapping example, we get a good time scale for these processes, which can be easily 10 years. I think you're still muted, Eric.
Sorry for that. So maybe one of the major hurdles of bringing this to clinical practice is also at this moment, still lack of standardization in the measurements, and the lack of benchmarks, of course.
That is also very true. Yeah, and also unfortunately the lack of standardization among vendors. Like we can't easily develop something on one vendor and use it on the other.
Yes.
So
do you see any progress in that area?
In the vendor specific area, there are some approaches, but it's I guess going slow. But it's also a hard challenge to face. I think other fields do much better in standardizing things. Everything that deals with post-processing, for example, I think became much better with XNet or similar tools to provide standardized information that can be processed in a pretty standard way. I feel like on the acquisition side, we're a little bit behind on this kind of.
Mm-hmm. Okay. Oh yes, I see a question here from Duccio Buccicardi. He says, is there any potential application in epilepsy brain imaging?
That is a good question. So the brain is my strong suit, and I'm not very well versed in the pathophysiology of epilepsy. I know people have done fMRI during seizure, which was very important to identify brain areas of seizure. But in the absence of an active seizure, I'm not entirely sure what would be best suited. I know of other studies which yielded interesting results, but more for the general overview of the disease than for like a patient diagnosis, is where tractography with MRI, like the connectomes as such, were used to study connectivity in the brain of epilepsy patients. But I don't think this is at the level of sensitivity where it can be used for single diagnosis. So I do have to pass a little bit on this one, I feel.
What do you think, Sebastian, are the most interesting domains for this type of quantitative analysis and biomarkers, besides the cardiac applications?
And so I think, because I'm strongly convinced of the first argument that I brought forward for quantitative MRI, that everywhere where we encounter diffuse disease, this is the way to go, because we won't be able to pick them up reliably by any other means. The heart is great because it's one muscle and very often is subject to diffuse remodeling. The brain, it's somewhat rare that you have a disease that actually affects the entire brain tissue homogeneously. Mm-hmm. So maybe this reason falls a little bit short in the brain for some applications. But there's other organs, the liver, for example, where diffuse changes are very common. And I think everywhere where we encounter diffuse changes, quantitative mapping should be our first line of attack.
Yes, and maybe also the spine, for example, diseases like multiple myeloma. This is also a system disease, of course, that could be interesting. Mm-hmm.
True, very true.
Yes. Okay, at this moment, I don't see any further questions. So again.
I think there was one more, which could be a biomarker for inflammation response by...
Oh, I missed that one, maybe. Yes, I have to scroll down and... Oh, yes, you're right. Sorry for that. Which could be a biomarker for inflammation response by processing diffusion MRI and ADC maps?
It's a good question. It's also, to be honest, a little bit out of my area of expertise. We do know that edema or the edematic response to inflammation and free fluid definitely has increased diffusion. So it would be dark in an ADC map because of cell death, less restriction to the diffusion motion is imposed. So it would show up as dark in the ADC maps. However, I think there might be tools that are more well suited for assessment of inflammation in the brain. For example, in multiple sclerosis, where we actually looking for these inflammation spots. And one of the images was actually from MS. T2 weighted imaging is very, very sensitive. So that might be a better choice than diffusion. But it's not my area of expertise. So I'm sure something can be drawn out of diffusion.
And maybe contrast enhancement could also play a role, the vascularization.
Also, definitely.
Yes. Yes, I don't see any more questions. One more, maybe. How do you see the, what kind of potential does artificial intelligence have in this, in using these quantitative data? How do you see the role for AI in this field?
So I was about to answer the reverse question, because I think the opposite is very important, that quantitative imaging is very important for AI.
Exactly, that's true.
The question how important AI is for quantitative imaging is mixed. There's a number of applications that already have to be proven very, very valuable. Traditionally, myocardial T1 maps were evaluated by drawing circles around the myocardium, which was tiring and annoying.
Yes.
And machine learning just performs great there. There's no reason for not doing this. So it definitely aids in parts of the steps. Also, reconstruction using machine learning gains great traction and bears great promise for all these methods to be much faster and much more sensitive. But I'm sure multiple other approaches will be proposed where the entire chain of quantitative imaging is elevated by machine learning.
Okay, I think, oh yes, I have one more question to finalize. So that might be a tricky one, but of course, we do see that combination of MRI and PET image, PET CT, or not PET MRI is increasing, the nuclear imaging. So do you see a lot of potential in that new development?
It's a good question. I think for the select disease models, it could be very interesting. There's a lot of push within the MRI community to obtain comparable information to PET with MRI itself. And I think that would be preferable for a number of reasons. But as we currently stand, a lot of PET offers great sensitivity for a number of disease, and like, for example, sarcoidosis in the heart or so, that is very worthwhile on a PET MR. Might change in the future when MR gets elevated, but also PET is improving, so who knows?
All right, thank you very much, Sebastian. I just want to thank everybody for having attended the session. And of course, the webinar will be available within a few days on the webinar platform. Sorry, on the USOMI platform, which is our society. I would also like to encourage everybody to have a look at our society webpage, usomi.org. And of course, everybody's welcome to join our society. Subscription fee is very low, so it should be accessible. And of course, the more members we have, the more potential we have to organize interesting lectures and webinars such as this one. I believe strongly in this kind of educational tools, and so every contribution is welcome. And of course, the more participants we have, the better. So thank you again, Sebastian, for this lecture. And I would like to conclude here. Thank the sponsor again, Bracco, and I would like to see you all again for the next webinar. Thank you very much and have a good evening.
Thank you. Bye.